All right, so part B of section 5. So we're still talking about limits at infinity. Let me pose the question to you. So the question I'm posing is, what is the maximum number of horizontal asymptotes that could exist? What's the maximum number of horizontal asymptotes? All right, well, time's up. If you think about it, since we have established that horizontal asymptotes are all about what happens in the end, right? The end behavior. So as x approaches infinity or as x approaches negative infinity, then when you think about it, there's really only two possibilities. There's the possibility is either there is no horizontal asymptote, there's one horizontal asymptote, which we've seen so far, or you could think of it as the graph is approaching two different horizontal asymptotes, one as it goes to positive infinity, one as it goes to negative infinity, right? So the maximum number of horizontal asymptotes that could exist is 2. Now, let me go ahead and spearhead a question of, well, look, if you mathematicians like to use all of this limit notation, then you go ahead and do it. I'm going to go ahead and use the pre-calculus technique because that is a lot easier. Well, I agree with you, and I think you should continue to use the pre-calculus technique, unless, of course, you're formally asked to use the notation of the limit. But let me make sure you understand something, that your pre-calculus technique is only going to work when you have rational functions. It's not going to work when you have non-rational functions, right? When you have things like what we have here, square roots in your denominator. Your pre-calc techniques are not going to work like that. So, and we do need to start thinking about the limits and how to approach it. Now, so let me go ahead and show you how you're going to do this. So it's going to be similar to the technique we used in part A. So it's going to be similar in that I'm going to take the 3x minus the 2 divided by, now I'm going to put a question mark here for just a second because I'm not telling you what we're going to divide by yet. And then I would also take the denominator, the square root of 2x squared plus 1. And that's also going to be divided by the same number. Again, I'm going to put a question mark as a placeholder. I'm not going to tell you yet what that is. Now, so what are we going to divide by? Well, let's look. Let's look at our denominator here. So we have the square root of 2x squared plus 1. Now, what we're going to do, and I'm gonna show you a trick here. What we're going to do is we are going to let x equal the square root of x squared. Right now, this is not a, by definition, the square root of x squared is equal to x. That I understand, but that is true for what? That is true for all x greater than 0. Now, don't you agree with me that the square root of x squared is equal to x? Right? You do. I hope you will agree with me that that is a true statement. But here's what you're going to do. You are going to divide by x, but you're going to divide by x here, and you're going to divide by the square root of x squared here. Now don't get lost yet. Okay? So let me go ahead and do that. So I said you're going to divide by x here. And indeed you're going to divide by x in the denominator as well. But a version of x that is helpful. Now, did I just divide by something different in the numerator than in the denominator? No, because the square root of x squared is x. So I am not altering my problem. I'm dividing by x and then dividing by x. But watch what's going to happen here. So let's start with the numerator. So if I have 3x minus 2 divided by x, that's just 3x over x minus 2 over x. Okay? And I'll clean that up in just a second. But there's the trick, or the reason why we chose to set the denominator up like this is, let's see if you can recall. If you have the square root of a over b, that can be rewritten as the square root of a over the square root of b. But likewise, that means if you have the square root of a over the square root of b, you can rewrite that as the square root of that quotient. And that is what we're going to do. In other words, we're going to have one radical instead of two. And what's going to go inside here is going to be the 2x squared plus 1 over the x squared. So do you see how we went from two radicals to one radical, just using that that definition, or that property? So let me go ahead and start to clean this up a little bit. So I still am trying to take the limit as x moves to infinity. The numerator, all right, so is going to just, well, 3x over x is just 3. So that's 3 minus 2 over x. And now let's clean up that denominator. So if you don't mind, I'm actually going to clean this up down here. So 2x squared plus 1 over x squared, that's just 2x squared over x squared plus 1 over x squared. So far, so good. So that's the square root of 2 plus 1 over x squared. All right, now let's bring that result over here. So that's the square root of 2 plus 1 over x squared. All right, well, all that work up front so that we can now evaluate the limit. And what do we get? Well, if you take the limit as x approaches infinity of a constant, we still get 3. So this is going to be 3 minus, well, 2 over infinity zeroes out. So it's 3 minus 0 over the square root of, well, the limit as 2 approaches infinity is still 2. But 1 over infinity squared is going to be going to 0. So are you with me that you get 3 over the square root of 2? That is the horizontal asymptote. That is the limit at infinity. At part B, I'm just going to give you the result. If you go back and you do the same thing, except now you let x, only now you let x be equal to negative square root of x squared for all x less than 0. If you go do the same steps that we just went through, you would find that the result is negative 3 over the square root of 2, and you should try that on your own to make sure that you can do that. Okay, so let me chat a little bit about limits at infinity for trig functions. Let's start with the first one, which is so we have 2 trig functions. Let's start with the easy one. So the limit as x moves to infinity for sine of x, well, look, your sine curve is going to continue to oscillate over and over and over again. This is never going to approach a horizontal asymptote, right? So in other words, if it just continues to oscillate between -1 and 1, this does not exist. There is no limit at infinity. Okay, so but now let's actually look at the limit as x approaches infinity of sine of x over x. And I'm going to use a little bit of geometry to show you why the algebra works. Okay? So, always a question. Should I start with the picture or should I start with the algebra? Well, let me start with the picture. So, we have 3 different colors. 3 different colors, and each represent a different graph. So let me see if I can draw you some pictures here. So this orange graph is sine of x over x. Right? And this purple graph is 1 over x. And finally, this green graph is negative 1 over x. Okay. So now this is an interesting concept. So there is the idea of the squeeze theorem or the sandwich theorem that you saw in a previous section, probably back in chapter 1, for sure. Basically, just without going back and writing the theorem in its entirety, basically says, look, we're interested in the orange curve, right? The limit of sine of x over x as x goes to infinity. But if you can sandwich that between 2 other functions who you do know the answer of the limit as x approaches infinity, if you can squeeze, right? See, do you see how the orange curve is squeezed between my 2 other functions? Right? This is what I mean. So we are going to be able to make a statement that, look, if 1 over x is going to 0 as x goes to infinity, and negative 1 over x is going to 0 as x goes to infinity, then because I can sandwich sine of x over x as x goes, I'm also going to be able to say that approaches 0. Now let's look at the more analytical side of this. So look, this is not bad. Do you agree with me? Right, you can look up here. Do you agree with me that sine of x, the highest it ever reaches is 1, and the lowest that it ever reaches is negative 1? Do you agree with that statement? Then, okay, so as long as if you will allow me that statement that sine of x is always going to oscillate between negative 1 and positive 1, well, that's great, but we care about sine of x over x. So what if I divide by x here, divide by x here, divide by x here? then that would mean that negative 1 over x, or sine of x over x, is always oscillating between negative 1 over x and positive 1 over x, right? But what does, if you let x approach infinity, what is negative 1 over x? What is negative 1 over infinity? Well, that's 0. What is 1 over infinity? Well, that's also 0. So hold on, are you ready? So if you tell me that sine of x is always between negative 1 and positive 1, and that sine of x over x is always going to be nestled between negative 1 over x and positive 1 over x, then by definition, if you let x go to infinity, that means that sine of x over x is always going to be somewhere between 0 and 0, which means what? Which means you answered your question. The limit as, let me go ahead and grab this, bring it down here. Let's answer the question. So that, no, that was an epic failure, wasn't it? Let's try that again. So that means that the limit as x approaches infinity of sine of x over x is also 0. All right, so we looked at using some trigonometry. What I want to do, right now is I think actually we're going to conclude right now. On another video, I'm going to show you the idea of infinite limits at infinity. But I've already shown you this in chapter 1. So let's go ahead and pause the video. I'll let you digest the information that we've gone over, and if we need to revisit infinite limits at infinity, we will in a later video. But as of right now, I've already shown you this back in chapter 1, so we're going to go ahead and conclude.